Hello everyone, nice to see you here. So my name is Ilia Semikolennykh and today I'm going to show you how to make a game using a notepad. By the way, does anyone of you have a notepad? Okay, I got to do it with myself. So about me, I'm a senior engineer at Ilia and 10 years in the industry already. And today we are going to discuss a pet project of my own that is an abstract concept. Like, imagine you crashed on the island and nobody is around. There are hundreds of thousands of kilometers or no one is there. No civilization, no job, no school, no house chores, whatever. I know what you're thinking. Finally, I got all the time in the world to play games.
No going.
But there is a catch. You have no games with you. All you got is a laptop with some Linux, not suitable for gaming. There's just this C++ compiler and that's it. You have no internet access to download libraries from internet, and what are you going to do? So let's define the rules of the game. Our main goal is to survive, meaning to make ourselves a game and play. We are going to use C++ 23 compatible compiler. In this case I'm using GCC, but it can be whatever else. It's rather new version. It's not an absolute must. This code is you can write the same thing in C if you want. And just the reason I'm using this latest version of C++ is that it helps making some things a bit more laconic. It's more expressive in its nature. We are not going to use any libraries. Oh, well, maybe with one exception. I lied to you a bit. We are going to use X11 because this is something that allows us to create a window on Linux and to read, send pixels there and read input from the player. That might feel like a bit of cheating, because I promised no libraries, but the truth is, if you have any system which has a display, let's say you got yourself an electronic pregnancy test or a fridge with a screen, chances are there is some piece of code that helps you draw pixels on the screen. So in this case, this is what we're going to use X11 for. We are going to abstract it away and not touch it anymore. The whole game compiles with just this command. G++, I called my game Stone Age for the reasons I'll explain later. O2 means maximum optimization. We're using 23rd standard, and those are these two and X11 libraries that we're going to use. Now, let's start with our first image class. This is what you would expect. The most naive way to write a struct for image. Just a two-dimensional array of B4 means byte 4. It's just pixel data, RGB, and alpha, which we are not going to use, but let it be there. And as you probably know, we can't put a variable inside of such an array in C++. And what you need to do instead is to dynamically allocate memory, but I'm lazy, so I just use template here, and it works. I2 is an integer vector. Now, let's put some pixels inside. Here's our main. This is the image you just saw. This is the game window. We are not going to discuss. It's my abstraction over X11. If you are porting this code to a different platform, let's say Windows or Mac or whatever, you just replace the contents of this particular class, and it's located in a separate file of code, but the main thing, the whole rasterization, the whole rendering, the whole game logic is still stays within this old file. For now, it doesn't have much. Every frame we perform this function. It's a lambda which just calls frame clear and just sets these pixels to these values. And then we just call window run and it displays the image, which in this case looks like this. It's just rainbow stairs to this dinosaur. Now, how do we do a rectangle? Of course, you all know how. It's just two for loops, which set the pixels and the coordinates to, let's say, red color. Here it is. So far, so good, right?
Wow.
But it's quite boring. It's not a game. It's, we have to do a bit more to be able to play it properly. What about non-rectangular quads? Can we do that? Yes. Let's switch our approach from integer pixel coordinates to floating points, limited in range from 0 to 1, clumped by screen coordinates, so we don't try to put anything outside the screen. And for every pixel center, we just get 4 edge values. I'll explain what the edge value is in a second. Here is the code. We start with the quad defined with these coordinates. Then we still go with these two form loops, but this time, instead of just putting our pixel values as we go in, we test if 4 edges produce a positive value. What means edge? What does it mean for an edge to produce a positive value? Imagine yourself an edge. This is a vector from here to there. Now you got yourself a point. You ask yourself a question: is it on the right or is it on the left? Is it orange or is it blue? How do you do it mathematically? For those who had linear algebra, mathematicians, they call it a cross product. But in fact, we are dealing here with a simplified case of that. We are in two-dimensional space. There are no crosses, no third coordinates. It just you take the corner case of this formula. You multiply these two vectors in a special manner, and here's the formula for that. Just take delta x, difference between this point and this, with along x, along y, is delta y, and the small one is to the orange point, the black one is to the end of the vector. You calculate this. If it gives you the positive value, it's meaning that you are going counterclockwise in your rotation, which moves this point here. Should it be the blue point, it would be clockwise rotation, and the value would be negative. Now repeat this for 4 times for every edge of the quad, and if every each of them tells you that it's on its right side, then you can pretty much be sure about this point to be within the quad. And here we got our animation showing how this whole algorithm works. It scans the rectangle which covers the quad and tests the edge values 4 times for every pixel, because brighter color or less brighter color on the left and on the right, and when we got the right value, the positive value, 4 times in a row, then we got our center quad painted as white. And here it is. Now, what we can do with our quad to modify it? Let's start with rotation. You can do rotation a number of ways. For this one, the most simple one is using a rotation matrix, which is throughout the program I'm using 4 component vectors. Those are how 4. They have 4 components, but the rest is trivial, 0 and 1. And matrices are also 4 by 4 due to that, so we can multiply them between themselves. They are compatible. And but once again, I'm listening only to first lines of the matrix. Here are zeros, we don't care about it, and the 2 additional lines are also the zeros. And then we multiply our quad by this rotation, meaning that we just go over every vertex in this quad and multiply the matrix by this vertex. And this gives us such a pretty animation. Our quad starts to turn each frame over around the 0, 0, which is located here. Because we move to coordinates with the 0 on the top, 1 on the bottom, left to right. But let's fix that. That's not a good coordinate set to work with. That's not very convenient, so let's move it closer to center. We could manipulate the coordinates in some sophisticated manner, or we should just once again use another matrix which is going to squish our scene by 50% and just add 0 5s to both coordinates, so the whole thing goes to the center. Now it starts rotating around the center. Now let's go 3-dimensional, because everything we've done before was just 2-dimensional, and we are going to make a 3D game. With no additional changes, just modify the rotation matrix this way. So instead of rotating our quad around the z-axis in x-either plane, it starts doing the same, very same operation, but in the xz line. How does it look? The quad starts turning around its axis, which is the vertical axis. The funny thing for me is that the mathematics works in such a way that, in fact, it just resizes this rectangle in both axes, but our brain, seeing that, says that it must be rotation around the vertical axis. I made the backside appear blue because with this approach where edge values give you all positive numbers, when they give you all negative, it means that you are looking at the same part but from the inside. So I had to add a special case there. Now, our quad is not very nice. It gets these rough edges. You can see it's quite kind of pixelated. Of course, I'm using lower resolution here, but those are very big pixels, not very nice. Let's fix that. Let's add multi-sampling to it. What is it is about? Normally, when you sample, meaning that you calculate all those edge values, you take the position of the center of the pixel. Right? It can give you only two outputs, either it is within your quad or it is outside. That's why there are all these staircases appear. Instead of one probe, you can get 4 or 8 or 16. You can really experiment with that. You can place those samples in a different configuration within the quad. Here I'm using so-called 4 rooks, which is why those samples there are located as you would put rooks on the chessboard so they don't attack each other. But in fact, there are many possible configurations. The better. The more random and chaotic your configuration is, the better. There are some approaches that change it every time and at randomness to it for better result. But we are just going to stick with this one. And then we ask our quad if this point is located within the quad. It's 4 edge matters, 4 times for each point, and then we mix the colors based on the result. If we get 4 points inside, 2 points inside, 2 points outside, then we just get 50% of the color, mix it with the background, and our quad gets this nice half-transparent pixels on the edge. Let's put things into perspective, shall we? Here is the simplified perspective projection matrix, which I will regret using later on, but when I was writing this, I didn't know about it. It's quite simple. The idea of perspective transformation is that you just divide by z coordinate. If your z coordinate points outside of the screen, the further something is, it gets scaled down to the center of your screen. If it gets closer to you, it gets scaled down. That's what we call perspective, right? So here's our 4x4 matrix. I invert Y just for convenience. I prefer Y pointing up, not down, as it's down in Windows systems. And here, everything we do, all we do is just we copy our z coordinate into the 4th coordinate of our vector, downward. Why? So later we can divide all coordinates of the vertex by this downward, because it's not 0. Don't divide by 0. And that gives us such a view. This is orthogonal projection, but now I hit a button and this is the very same scene that's rendered with changed projection. We divide by z, and this is how it looks like. Now, our scenes were stationary in such a way that we couldn't really move around that. We need to invent a camera so we can go around our scene and look at this from different angles. Now, there is no camera per se in this in our code. We always render assuming that the observator sits in the beginning of the coordinates, so 0, 0, 0, and looks along the z-axis. So instead of changing that, we are going to change the world around us. We're going to turn the world around us literally in the opposite direction that we would like to move ourselves if we were. Think about it in a way that you take 5 steps right. It means that the whole world takes 5 steps left. If you turn clockwise, the whole world turns counterclockwise in relation to you. And that's what we're going to do. Camera is always in it's a human term for mathematical abstraction, which just means inverse transform for the world. Here we got ourselves an identity matrix. Oh, this part's not real identity, but it's okay. And here I'm putting time as a negative time as a value which transforms the z coordinate. I'm using column measure, so the line should be read as x, y, z, the fourth coordinate down there. So everything I do is adding the negative time to all z coordinates in this scene. And that gives us such a slide. Oh, but
What happened? It wasn't like this.
it wasn't planned like this. The reason we see it this way is that our mathematical model, our render, it doesn't have a concept of something being behind you, right? We just said quads to be rendered. If they are in front of us, they get scaled, everything is fine. If they are behind us, they get scaled by these negative values. It's still okay, they will be rendered. It all depends on just the order that you send them to the render. And so we got, basically we got our rear mirror view into our main view. How do we fix that? Well, if every z coordinate is negative, just discard it and let's say continue. And that will work for now. Now let's make our camera a bit more agile, for the lack of a better word. We want to be able to rotate, to move around. What is the idea on how to implement that? Using the same approach as I showed just before, it means that we have to find the inverse transformation for the kind of transformation that our camera has. If our camera is on the right, we move the whole world to the left. If it rotates, we rotate backwards. In terms of matrix mathematics, it means that we have to find an opposite matrix, an inverse matrix. This is just a matrix. This is an inverse matrix. 1 multiplied by another gives us 1. And here's the formula how to find the inverse matrix. Usually it will involve a lot of calculations. You can't find inverse matrix for any matrix because for the same reasons as you can't divide by 0. Sometimes matrices they can also be they can contain some values, but if some key values combinations become 0, it means that this is the matrix-like object of which represents 0, even though it's a matrix. Then you can't divide by 0. So not every matrix is invertible. Usually, inverse matrix involves a lot of operations, but now we can approach it using a different conception. We have. It's not just a matrix. It's not just random symbols for us. This is the transform matrix for our camera. If you assume that C and S are cosines and sinus of angle, which we use to rotate our matrix, then it looks like this, right? We don't rotate along the x-axis or along the z-axis. We don't do this. Don't do this. We only do this.
And
Yeah. Let's be realistic about our game. It's not going to be Starship simulation. So, this is what it is. And we can write down multiplying this matrix by something, some unknown values, and then solve this system of equations to find the opposite inverse transform. Or even better, we can just think for a bit.
No.
What is an inverse transform? What does it mean? It means that if you rotate it clockwise, then we rotate counterclockwise. This is the part that rotates. And this 3 by 3, it scales, but it also rotates. What does it mean to rotate something in a different direction? Just change the sign. Cosinuses stay the same because angle becomes minus angle. Cosinuses don't care. Sinuses, they change their sign, the rest is the same. Now we only need to find these translation values, because we also want to do this thing when we shift the world in the opposite direction. I'd like to tell you that it's just -x minus y minus z, but it's not that easy, because it was rotated, right? The camera goes somewhere and then rotates. It means that you need to rotate around that point backwards where it used to be and shift backwards. So you take this, multiply it by camera inverted x and z coordinates, and you get what you call an opposite translation. So let's walk. Oh, there's another problem. Now we can see through all these columns when we look in the opposite direction. Why is it so? Well, because there is no depth in this scene. All we did up to this point is just divide by z. If it's negative, then discard it, and that's it. After that division by z, we just don't care about the z. We just draw plots as they go along. So if something happened to be drawn later on the later stage, then it just overwrites our picture. So we need to invent depth. And answer ourselves a question: how far is the pixel from the screen? It involves some 3D math, but for simplicity, I just put it into 2D perspective for you. Imagine that this is your Y, X goes somewhere here, but we don't care about it, and here it holds Z. So, we got ourselves the quad, which is located in something like this. This is the plane of the quad, and here it is. And we look at this part. Our screen goes here. We imagine ourselves a line going from the screen through this quad, piercing it like an X-ray. We already know which coordinate Y is this. Our goal is just to find the Z. As you probably know from the school, the equation for this line is y equals x plus b. In our case, it's not x and z, but also y equals y0, because we already at this point we know the location of the pixels that are in. So it's solved like this. A bit more complicated in 3D case, but not very complicated. And we got ourselves the Z. Now let's take a walk, and what the hell is wrong with this floor? Oh my, no, not like, oh. it was perfect until it wasn't. One thing I suppose I forgot to tell you. First time I did this trick, I got everywhere just once. Every z coordinate, every depth value was just 1. I scratched my head and remind myself that yeah, I think I divided all coordinates by z, meaning that I divided z by itself, meaning that all my quads are now located on the distance of 1 to the camera. Genius. So my naive solution to this problem was just to I'll divide just x and y and leave that alone, and it will work. Spoiler, it didn't. And I had to eventually fix the projection matrix to a bit more complex form to remap that between far and near flipping planes and divide by W, all according to the book, and then it started working. But still, there was another problem with the floor. Imagine rendering on the floor. Imagine yourself, you got yourself a quad. Here's X, here's Y, here's Z. It's like it's perspective transformed. Small here, big here, it's okay. Now what happens if you start moving your camera along this quad? And those points, they cross this 0 coordinate of Z. Z becomes negative. And your floor does this. I'd like to demonstrate you how it's supposed to look in the video, but the truth is this form doesn't even render, so your floor just disappears, and that's it, you're left in the empty space. Now, what's the solution of this problem? We need to cut the quad. Let's pick any arbitrary non-zero value along the x. Call it the near cutting plane. Now, it can go something like this through our quad and cut it into 2 halves. I think you can already see the problem here. Let's cut and let's count the points together. 1, 2, 3. That's not 4. 1, 2, 3, 4, 5. That's even worse. So, this was the moment when I started questioning my life choices, which led to this. Because we need to count the quad, and I was angry at myself that I decided to go with the quads at the first to begin with, because cool guys at NVIDIA do it with triangles. So there was some math involved, and yes, there as much as 2 new quads can arise from cutting a single quad. That will be important later. All right, now I feel some of you might feel embarrassed at this point, just for a bit. Probably some experienced programmers in this room, they are sitting and thinking, all right, Ilia, this rasterization, it's an embarrassingly parallel problem. What is the reason? Why do you embarrass us by rendering all these pixels one by one in a sequential manner? For those of you who don't know, it's the embarrassingly parallel problem means that this is naturally parallel problems. You just give it to as many workers as you have, and every pixel can be rasterized separately from the others. You don't have to do it one by one, you just can parallelize it. So I decided to work with the test scene, which contains this many columns. The frame time was around 28 milliseconds on my i7 12700K processor. Now, how do we parallelize it? Well, we need to separate the work between the working threads and make sure they don't ever attempt to write to the same place. So we cut our picture at such tiles and assign every thread its tile and let it just draw this particular tile and that's it. But apart from that, they all want to have access to all the quads which are there. It would be nice to, yeah, I don't have much time, so let's assume you just did it, okay? There was a lot, we just did it. So we just put some barriers there and there, just some sequential code, then parallel, then again, and then our 20, then it looks like this because I screwed up with the math, and these tiles, those were the tiles. But then when I finally saw this picture again, 20 working threads instead of one, 28 milliseconds in the beginning. Now, obviously, it goes down to 14. Because, well, it's not that inversely parallel as I was thinking, though later I managed to cut it much lower. Now, the boring part is behind us. Let's make the game. Draw some cactus in Blender, put it into Obj, import it to our engine we just wrote, add, calculate normals, calculate the dot product to light, add lighting to it. Here's our lit cactus. Let's put a dinosaur into it. Here it is. Let's make them march and dance. And here's the demo time. I just got a few minutes, so I'll be quick. Let's compile our game and run it. And here it is. We got ourselves a field with dinosaurs. They jump across the cactuses, and we even can throw rocks at them. Now he's angry at us and tries to chase us. If he catches us, he will just bump into us and try to put ourselves onto the cactus. But we can continue hitting it with rocks. So it goes away. Now it runs away. That's it. Oh, questions, please.
Jak będzie multiplayer?
Wolisz grać jako dinozaur? Czyli rzuca się kamieniem lub być rzucany?
Być kamieniem.
Tak, proszę.
Gdzie jest dinozaur?
Oj, tak, przepraszam.
Okay, so I have one.
Yeah?
How is it to go if you had libraries?
Okay.
How easier you could get if you had access to libraries?
It depends on the libraries, right? There is such a library called Unreal Engine. You can do it in a matter of minutes there. Well, yeah, well, it's more like a framework, right? Once again, depends on the libraries. There are those graphical engines, there are game engines, there are also these graphical APIs, right? You can try to do the same thing using, for example, DirectX, or OpenGL, or SDL, or Vulkan, if you like to hurt yourself in the past.
Right. Life is another one that will.
So yeah, it's full of different challenges of a different kind. but some of this work they do it for yourself. For example, I was horrified with this parallelization thing and this cutting the quad thing, which graphics cards just they don't ask you. You don't configure it in DirectX, OpenGL, Vulkan. You just don't know it exists. They do it automatically for you, and of course it gets much simpler.
Okay, alright. So I have another one.
Yeah.
I'm talking already. Are you already thinking about porting into like a microwave or something? Like a Doom?
Yes.
I would like to see it one day.
Alright, if there are no more questions, then once again, thank you for attention.